Well, we're hitting our last chapter now, which sounds great, but remember, the one set of notes from chapter 21 gets combined with this one and one more coming for chapter 22. So let's talk a little bit more about light rays, and today we'll focus on light behavior and colors, and next time, which will be the last time, we'll talk about things such as reflection, refraction, and diffraction. All right, here we go with light and color. Ready? You see, it's pretty short, only 6 to copy this time. Visible light is radiant energy that we can see. Okay? And visible light is actually 7 colors of light that all come together and make what we call white light. Red, orange, yellow, green, blue, indigo, and violet. And when those all come together, the frequencies and wavelengths become a beam of white light. Okay, now you see on there that light, and we said this before, light can travel to Earth through outer space. Light does not need a medium. Remember that sound does need a medium, but light doesn't. And that's great because that's how the sunlight gets from the sun to the Earth. And remember, it takes approximately 8 1/3 minutes, so 8 minutes and 20 seconds. Now this is the frequency range of the red light to the violet light, and of course the other colors in between. Now that's 10 to the 14th, so that is 13 zeros after the 8 if we were to move that decimal point. If we count 13 spaces, we're going to get all the way to this 5 right here. So imagine all these characters, including the spaces, being zeros. That is how big the frequency of red light is. Now, same idea here. Violet light, 7.5 times 10 to the 14th. 1, 2, 3, 4, 5, 6, 7, 8, 9. You have to add about 4 more characters, so you're right around over here. That's how big of a frequency violet light has. All right, 2 definitions for you. Luminous. This is anything that gives off its own light. Think of the sun. Well, the sun gives off its own light, and that radiation travels through space into the Earth's atmosphere, and then we can see. Now remember, light, let me say it this way. We cannot see anything until light bounces off the surface. That's why we can't really see light beams too much, and I'll demonstrate that in class. But anything that gives off its own light, the sun, think of when you turn the lights on when you walk into a room, those light bulbs are luminous because when electricity runs through those, then the bulbs will give off their own light. Now think of the moon. That moon does not give off its own light. The moon reflects light from the sun, so whatever other source. Reflectors in the road. Okay, at night, especially, those reflectors in the road help us see the lanes a lot better. Anything that reflects light from another source is illuminated. So the headlights on the car are luminous and the reflectors are illuminated. And there's reflective paint also on the roads to help us see the lanes a lot better. So anything that reflects light is called illuminated. Anything that gives off its own light is called luminous. Ready? Now you don't have to copy this page, just take a look at the picture. Now from left to right, these are in order of shorter to longer wavelength. So gamma rays have the highest frequency of all light waves. However, gamma waves have the smallest wavelength, that's 10 to the negative 14th. Radio waves, FM, TV, shortwave, and AM, those are all kinds of radio waves. Those have the lowest frequency but the longest wavelength. That says 10 to the 4th right there in meters. That's 10,000, so 10,000 of these meter sticks. That is how long a radio wave is. That's very long. Remember, light waves are transverse. Now, look at the visible spectrum. You see it's a very small portion of the entire electromagnetic spectrum. From frequency, red, orange, yellow, green, blue, indigo, violet, but from wavelength, violet, blue, or indigo, blue, green, yellow, orange, and red. So they're actually backwards of each other. And again, that's because high wavelength means low frequency, high frequency means low wavelength, and high wavelength means low frequency. All right, we'll talk more about that as we do assignments. Ready? And the types of light. Incandescent. Think of just turning on the lamp. You might have a reading lamp that you turn on so you can read your page better. Now, these bulbs get very hot. That's because most of the electrical energy that goes in comes off as infrared light, and infrared light carries a lot of heat, and only a small percentage of the electricity gets converted into light. Now, those are very hot, so don't touch a burning light bulb. Now, there are others that are much more energy efficient and cooler to the touch. In recent years have been made, but older style incandescent bulbs very hot. Up in the ceiling in the classroom and pretty much any commercial building, you'll have fluorescent lights. Turn on the electricity. The photons cause mercury gas that is inside those bulbs to glow, and that glows white light. And those bulbs, fluorescent bulbs, use much less energy because most of the electricity that goes in actually becomes light, and those bulbs are much cooler to the touch. They're actually very safe to touch. These bulbs cost more to purchase but use less energy over time. So if you're trying to rewire your house, ask yourself, do I want to pay more up front but pay less over time, or pay less up front for incandescents that'll get hot and I'll actually end up paying more in my bill over time? Now, think of things like glow-in-the-dark stickers. These things are called phosphorescent. Glow-in-the-dark stickers are just one good example. These things will absorb sunlight or artificial light from lamps and lights in the ceiling and store that energy until it gets too dark. And once it's dark, that energy leaves the sticker or whatever the phosphorescent thing is and start to glow. And we can use those to help see our way around. They're not going to shine light a long distance, but they'll help us and they'll help other people see us in the dark as well. Halloween, you see a lot of kids with the glow sticks. Those are phosphorescent. Some chemicals, after you break the seal in between, give off that glow just like the glow-in-the-dark stickers do. Ready? Light rays. Yeah, I'll put this up here and go ahead and fill the screen. Think of a highway with cars on the highway. Okay? Actually, I'll start with ray. A whole bunch of cars going along the highway all in the same direction. That's called a ray. The highway itself on which the cars travel, that's like the beam. So we get a bunch of rays all going in the same direction from the same source. We call that compilation a beam. So the rays are like the individual cars all going in the same direction, and the beam is like the highway on which the cars travel. So a beam is like the highway on which rays travel. So many rays make up a beam of light. Hopefully that made sense the way I said that. But the rays are individual, and the beam is a compilation, a gathering of all the rays all going in the same direction. And of course we use an arrow like we would use an arrow to show any direction. All right, ready? Transparency. Well, 3 words here. Transparent means light passes through easily so we can see through. We look through a window. A window is made of glass, and glass allows light to very easily pass through. And we get good, clear images on the other side unless there's something wrong with the glass. So anything we can easily see through, we call transparent, which means light passes through easily. Now, there are some things like stained glass or shower doors in which some of the light, not all, will travel through and some of the light is blocked, and there may be some bumpy shapes and curves on this window or this piece of glass or plastic. And what happens there is the light gets scattered. So if we are able to see something on the other side, that image would appear fuzzy and not very sharp and be a little tougher to tell what's behind the other side. So stained glass windows will do that, the coloring will. Many shower doors have really curvy, bumpy textures to make them translucent so it's hard to see through. Now, things that block light completely are called opaque. We can't see through those things. We can't see through the wall. We need a window in the wall or some kind of opening in order to see through. So just 3 definitions here. Transparent are things that let light pass through and we can see everything well. Translucent, some of the light goes through but gets scattered, and what we see, if we see anything good, is really fuzzy. And opaque blocks light, we can't see through, and this is the reason we get shadows. get the sunlight coming down, hitting our bodies or hitting something that's in the way of the light, and we get a shadow on the ground or on the walls. Those are called opaque. Ready? All right, a couple pages left. Told you this was pretty short. Additive primary colors, and notice I put light right here. What are these colors? Red, green, and blue. Your primary colors of light are called additive primary colors for a reason. When we add the frequencies of these colors together, what we get is white light if we add all three together. Now look what happens if we add red and green together evenly, we get yellow. Red and blue together evenly, we get magenta. And blue and green together evenly, we get cyan. I want you to pay attention to these colors, especially for the next page. Yellow, magenta, cyan. Red and green, light, make yellow light. Red and blue light, make magenta light. And blue and green light, make cyan light. And every color we see comes from combinations of these three. Okay, maybe red is more than green and so on, so we get different shades of yellow, and different shades of the colors have different names as well. If we combine all three of these together evenly, we get white light, and this is very easy to demonstrate in class. I have a small machine and an overhead projector, and we can easily see what happens when we mix the colors of light. The additive primary colors, again, they're called additive because when we add the frequencies together, we get these colors, and if we add all three, we get white. So white is all three colors of light added together. One page left. Ready? All right, before I put the words up, I want you to pay attention to what I said on the last page. By combining red, let's back it up and show you, red, blue, and green, any two of them evenly, we got yellow, cyan, and magenta. Look here again. These are the colors of pigments. You ever look at a printer cartridge? 3 different colors in there. Magenta, cyan, and yellow. And look what happens when we subtract the frequencies that enter our eyes. And when we combine, we're talking pigments now, paints. We combine magenta and yellow evenly, we get red. We combine magenta and cyan evenly, we get blue. And when we combine yellow and cyan evenly, we get green. But look what happens when we combine all three of those evenly, we get black. Other colors come from these. So if you want to print a color paper or a color picture, what the computer will do is put just the right amounts of each of these colors to give us the colors that we end up seeing in any particular spot on the page. And combining all of them evenly will give us black. So someone has to program that computer perfectly to mix the colors in that ink cartridge together. And this is why you might run out of one color before you do another. Okay? You're using the color printer, you got your paper, you have to print it and turn it in, not electronically, and suddenly starts printing red. Why? Well, red is a combination of cyan and yellow. What happened is your cartridge ran out of cyan ink. So magenta and yellow, really, I said it wrong, magenta and yellow will give you red because you're out of cyan ink, and you'll see red on your paper now. Same idea if you run out of yellow ink in that cartridge. You'll have magenta and cyan, and you'll end up with blue, and the same to get the green, you ran out of magenta. Right, black is all three combined, and every other color we see is a combination of these three. All right, that's going to do it. Here's the funny the end joke. What a colorful lesson we had. One more set of notes coming your way next time. See you then.